First off, of course, thank you to the organizers for inviting me to participate in this wonderful conference. And also, I'm coming from California. I'm a bit jet lagged, so I want to thank the other speakers for giving really interesting and engaging talks. I hope I can do the same. Today I'm going to be telling you about research I've done examining the neural contributions at a circuit level to an accumulation of evidence decision-making task. And let me introduce this by way of example. I'm a parent, and so when my kids were younger, I was often woken up in the middle of the night by mysterious sounds. And when this occurs, I was essentially faced with a binary decision about who was making these sounds because I have two kids. Was it my younger son, or was it my older son? And it helps to sit and listen to the sounds for a period of time and essentially accumulate evidence for each of these two hypotheses. For instance, if I hear something that sounds more like crying, that favors my younger son as a source. And if I hear something that sounds more like sneaking a cookie from the kitchen, that favors my older son as a source. And the more sounds I listen to, the better my accuracy will be in making this sort of decision. Much of my research has focused on trying to understand the neural mechanisms that underlie decisions such as these that involve the combination of information over time. Here's an outline for my talk. First, I'm going to start with some background just to motivate the basic questions I'm addressing during the rest of the talk. Next, I'll tell you about previously published work looking at the contributions of the posterior parietal cortex and the prefrontal cortex during an accumulation of evidence decision-making task in rats. And finally, I'll tell you about newer, not yet published work applying the same set of tools to other brain regions, including the superior colliculus and the dorsal striatum. And I think some of the most interesting results I've come across have come from these later experiments. So let me start with some background. A common feature of decision-making is that hard decisions are often slow and easy decisions are often fast. And this applies to a variety of different types of decision processes, including value-based decisions, memory-based decisions, perceptual decisions, and others. A common core process that we've talked about a little bit already, noisy accumulation of evidence, can account for this feature in all of these different types of decision-making processes. At least there's examples in each of these different cases. And the way this noisy accumulation framework works is you have an evidence accumulator. Here I'm describing it in the context of a binary choice between right and left. Evidence that favors a rightward choice adds to this accumulator. Evidence that favors a leftward choice subtracts from the accumulator. At the time of decision commitment, the sign of the accumulator dictates the choice. If it's positive, greater than this decision border, the choice is rightward. If it's negative, less than this decision border, the choice is leftward. This class of models often also invokes decision bounds, as illustrated here at positive and negative B. And if the evidence accumulator ever reaches either of these two bounds, it results in immediate decision commitment for the corresponding choice. The example trajectory that I'm showing you here comes from a trial with weak, unreliable evidence overall. And so sometimes the evidence favors rightward, sometimes leftward. That results in a lower slope, and this can explain why hard decisions are often slow. In this case, the trajectory has not yet reached either of the two bounds. In contrast, here's an example trajectory that comes from a trial with a stronger, more reliable evidence. The evidence more consistently favors one choice over the other. That results in a steeper slope. The bound is reached more quickly, and this can explain why easy decisions are often fast. In this class of models, individual trials meander along noisy trajectories. I'm showing you a bunch of example trajectories here that come from different stimulus difficulty classes. Basic trends can be revealed if we average across many trials within each stimulus difficulty class, and the resulting averages exhibit this ramping response profile with slope that depends on stimulus strength. And intriguingly, similar patterns of responses have been observed in areas of the monkey brain when animals are making decisions based on the accumulation of evidence over time. In some of the first experiments demonstrating this, neural responses were recorded in area LIP within the posterior parietal cortex of the monkey brain when animals made decisions about the direction of a noisy dot random motion stimulus. In here I'm showing you population responses recorded in this area of the monkey brain during the period of decision formation while the animal is deliberating. And what you can see is that after a delay, these responses exhibit ramping response profiles with slopes that depend on stimulus strength, very much reminiscent of the average trends of evidence accumulator models. And this has led to the suggestion that areas of the brain that exhibit this characteristic of response may be involved in a neural implementation of evidence accumulation. Today I'm going to tell you about work I've done to examine this idea more carefully. And in particular, I've done this work in the context of an evidence accumulation task developed in the Brody lab, where rats accumulate evidence from auditory sensory stimuli. The way the task works is that rats are placed in a behavioral box with 3 nose ports, one on the left, one in the middle, and one on the right. Trials start with the illumination of an LED in the center port, which cues the rat to poke its nose there. After it does, auditory stimuli are played from 2 speakers, one speaker on the left and one speaker on the right. These stimuli consist of sequences of clicks that are generated by Poisson processes with different rates for the 2 sides. And the rat's task is to determine which side played the greater number of clicks. We control the stimulus duration as an experimenter, and we use a range of durations. And when the stimulus ends, we turn off the central LED, which serves as a go cue, indicating to the rat that it can respond with its choice. The rat does so by making an orienting movement either to the left or right nose port, and it gets a water reward for correct responses. So I'm going to show you a video of a rat performing 2 consecutive trials of this task. I'll also overlay on the video the side favored by the clicks, because I'm going to play them through the speakers here, but I'm not sure if you can hear them, and you definitely can't distinguish left and right. So here we go. Trial difficulty is controlled by adjusting the ratio of right to left click rate. So for instance, a ratio of 39:1 is very strong evidence. This is an easy trial. A ratio of 21:19 is much weaker evidence. This is a more difficult trial. After training, rats perform this task quite well. This is an example psychometric function from one rat showing the proportion of rightward choices as a function of the number of right minus number of left clicks. And what you can see is when there's a large excess number of rightward clicks, these positive values here, the rat chooses right quite frequently. When there's a large excess number of leftward clicks, these negative values here, the rat chooses right less frequently, it chooses left more often. And it more evenly distributes its choices at intermediate click differences. So the rats are using the clicks to inform their choices. In addition to controlling stimulus difficulty, we also control stimulus duration, as I told you, and this shows proportion correct as a function of stimulus duration, sorted into different stimulus difficulty classes. Red for a large click rate ratio, blue for a more evenly balanced click rate ratio. And what you can see is that, not surprisingly, rats do much better for these easy red trials than these more difficult blue trials. But in addition, within each stimulus difficulty class, performance improves as a function of stimulus duration, which is one hallmark of accumulation of evidence over time. To really nail down accumulation, the Brody lab had also developed a detailed behavioral model that I'll tell you about later in the talk. And from this model, we can estimate the time constant of integration of sensory evidence, and it reveals relatively long time constants in this task. So this is exactly what we want, a task where the rats are accumulating evidence over time, so we can try to understand the neural responses that support that process. But where should we start looking in the brain for neural responses that may be involved in evidence accumulation? And in this, I was guided by the foundational research that was done in monkeys, showing ramping responses in multiple different brain regions during evidence accumulation tasks, as I showed you before, for PPC here on the left, but also in other brain regions, including the frontal eye fields, or FEF, here on the right. And again, this pattern of responses has led to a suggestion that these brain regions may be involved in a distributed fashion in the evidence accumulation process. However, there are a number of important questions that remained unanswered based on this foundational research. Among those was, how is accumulated evidence specifically encoded in these regions? Is it similar? Is it different? Are these regions causally necessary for task performance? And if so, when does their activity matter? To begin to address questions such as these using our rat model system, I started by looking in potentially homologous regions of the rat brain, PPC, and an area called the frontal orienting field, or FOF, with coordinates shown here. So this is a top view of a rat brain, this is the front, and this is the back. These areas share many important characteristics with monkey PPC and FEF that led to the original targeting of those areas for signatures of evidence accumulation, which I'm just summarizing here. So that's really what motivated us to start with these regions. In describing the results that I found, let me start by describing the selection criteria I used to identify neurons I thought were most likely to be involved in evidence accumulation. The responses here I'm showing you come from an example neuron that I recorded in PPC, but there are similar neurons in FOF as well. And I'm showing you the responses aligned to two different time points of the task: stimulus onset here on the left and stimulus end here on the right. The top rows show rasters where each individual row is a trial. Each of the tick marks here is the time of an action potential or spike on the trial. I've sorted the trials based on the choice the animal made: red for anti-preferred direction choices, blue for preferred direction choices. During an actual experiment, of course, these trials were interleaved. And then the bottom row shows the PSTHs, or the average responses. Actually, more specifically, it shows the standard error of the mean response with each of these different lines of the same color. And what you can see is that for this neuron, already early during the stimulus presentation period, there's a clear difference in responses for trials that will subsequently end in preferred direction choices compared to trials that will subsequently end in anti-preferred direction choices. And importantly, this is occurring well before movement initiation, which typically happens around 150 milliseconds after the end of the stimulus. So because this neuron has selectivity during this period of deliberation, we thought that these were the types of neurons that were most likely to be involved in evidence accumulation. And for the rest of the talk, I'll focus in on neurons such as this that have significant pre-movement side selectivity. That constitutes 23% of the neurons I recorded in PPC and 32% of the neurons that I recorded in FOF. The first thing that I examined for these neurons was their dependence on stimulus strength, and that's why I'm showing you here for the 93 pre-movement side selective neurons in PPC that I recorded. This is normalized firing rate as a function of time from stimulus onset, not including any part of the response after the movement. I've sorted the trials based on the stimulus that was presented: green for preferred direction stimuli, red for anti-preferred direction stimuli, the darker hues on the outsides for stronger stimuli, the brighter hues in the middle for weaker stimuli. And what you can see is that after delay, these responses have ramping profiles with slopes that depend on stimulus strength. Stronger stimuli lead to more extreme slopes, and weaker stimuli lead to more intermediate slopes. We can also apply the same analysis to FOF. And in FOF, there are some differences, but it still has this important response characteristic of ramping profiles with slope that depends on stimulus strength. The punchline of these results is that they establish that rat PPC and FOF have this important response characteristic in common with monkey PPC and FEF during evidence accumulation tasks. Now, remember that this pattern of responses has led to the suggestion that neurons such as this may be involved in evidence accumulation. And again, the reason for that is the resemblance of this pattern to the average trends of evidence accumulator models. Now, this approach to understanding neural computation, I think, has been extremely fruitful in the domain of decision making, but at the same time, there are limitations to it. And in particular, it doesn't take into account information about individual trial trajectories. So for instance, these two red traces here will be treated together because they come from the same stimulus difficulty class, even though they have very different values of the accumulator at this moment in time. And likewise, this red and this green trace here will be treated separately because they come from different stimulus difficulty classes, even though they have similar values of the accumulator at this moment in time. If we had more information about the trajectory of the accumulator on individual trials, we could do more intelligent trial grouping. Unfortunately, work from the Brody lab afforded us with exactly that. The lab had developed, as I alluded to earlier, a detailed behavioral model that provides estimates of this accumulator value as it evolves on individual trials. The way the model works is it takes into account information about the precise timing of clicks on individual trials to estimate the distribution of the accumulator value as it evolves over time. So in this plot, this is one trial. The green triangles on the top show the times of rightward clicks. The red triangles on the bottom show the times of leftward clicks. And the main part of this figure is a heat plot of the distribution of this accumulator value as it evolves over time from left to right. Right clicks push this distribution upward or more positive. Left clicks push it downward or more negative. And the model also takes into account multiple sources of noise, as you can see with the broadening of this distribution, and a number of other parameters that can be demonstrated to affect decision making in this task, including the time constant of integration, as I alluded to earlier in the talk. The key insight that makes this model really useful for understanding neural responses is that we can use the model to relate accumulator value to neural firing rate to generate tuning curves for accumulated evidence. Tuning curves are a basic assay that relate firing rate to a variable of interest, but they had not previously been estimated for this variable accumulated evidence. So let me show you the method that we use to generate these tuning curves. This is a similar schematic as I showed you on the previous slide, except I've rotated the axes so the accumulator values along the horizontal dimension and time proceeds upward along the vertical dimension. And again, this is the estimate of the accumulator value from the model on one individual trial. I also recorded a neuron in PPC on this trial, and this is the response from that neuron. And what I'm going to do here is to relate these two quantities at each moment of time into the decision process. Consider 1 moment of time, 400 milliseconds into the process. I have the estimate of the accumulator value, and I have the neural firing rate. And I have that for other trials as well. Here's a second trial, and here's a third trial. By combining across trials, I can look at this relationship. Firing rate is a function of accumulator value for this one neuron in this 1 moment of time. This is a tuning curve for accumulated evidence. I can also repeat the same procedure at other moments of time to look at how this relationship changes. I'm going to build up a figure showing that step by step. So now I have firing rate as a function of time. I'm showing you one vertical slice through this figure corresponding to 400 milliseconds, the same time point that I was showing you here on the left. And in fact, this is the same exact data as I was showing you here on the left, except now the accumulator value is represented entirely by the color. If I fill in the rest of this plot, you can see how this relationship evolves as a function of time for this individual neuron. I don't want to dwell on this one neuron. I'm just showing you this as a way of showing you the method before applying that method to the populations of neurons that I recorded in these brain regions. So starting with PPC, there are a number of interesting things that come out of this analysis. The first is that there appears to be what I would call a graded representation of the accumulator in PPC, and what I mean by that is that for each of these vertical slices, there's a roughly linear mapping between accumulator value, the color here, and neural firing rate, the position along the y-axis. Second, this encoding is fairly stable. These lines are relatively flat, so to give a more concise picture of the encoding, I can take the average across time to generate this time-averaged population tuning curve. And here it's even more apparent that this relationship is pretty close to linear in PPC. And what this means is that this measure of activity in PPC gives us a fair amount of information about the graded value of the accumulator. So our interpretation of this is that PPC has sufficient signals to be involved in the accumulation process. And admittedly, this interpretation is not very different than the interpretation of ramping signals that have been observed in monkeys during evidence accumulation tasks, but I think it shows it in a more rigorous way. And the fact that it's more rigorous becomes apparent when we apply this analysis to other brain regions. Remember that ramping signals in other brain regions have led to the suggestion that they may be involved in similar computations, and now we're in a position to test this more carefully for rat FOF, which also had this ramping characteristic. So first, when we apply this analysis to the population of neurons in FOF, there are a number of similarities with PPC. The first is that the encoding is fairly stable. These lines are relatively flat. If I look at the time averaged population tuning curve by averaging across time, you can also see that this relationship is monotonic. Lower values of the accumulator are associated with lower firing rates. Higher values of the accumulator are associated with higher firing rates. I can compare directly between these two areas by plotting them together on the same figure, which is what I'm doing here for PPC in black and FOF in red. And you can see that FOF has a less linear and more step-like relationship with a sharper transition from low to high firing rates. And where this transition occurs is also interesting. Remember that in the model, we have a decision border, and if the accumulator is greater than this decision border, the choice is rightward. If it's less than this decision border, the choice is leftward. And this zero-point decision border is exactly where the transition between low and high firing rates is occurring in FOF. So rather than preserving as much information about the graded value of the accumulator, it seems as though this population average activity in FOF instead reports something more closely linked to the choice that should be made based on that accumulator value. So under this idea, the FOF is essentially reporting a continuous answer to the question, if the go cue comes now, what do I choose? Now, this pattern of responses naturally leads to a simple interpretation that perhaps PPC is critically involved in evidence accumulation. FOF reads out that accumulated evidence to report something more closely linked to a provisional choice that then guides behavior. And that would be nice and simple, and I hope that was the case, but it turns out to not be that simple. Let's start with PPC. If PPC were a critical node for evidence accumulation, then an activation of PPC should have clear effects on behavior, and it turns out that's not the case. These experiments were led by another former postdoc in the Brody lab, Jeff Ehrlich, who now has his own lab at NYU Shanghai. And in these experiments, we infused PPC bilaterally on both sides with the GABA agonist mucimol so that we could reversibly inactivate responses in this brain region. And what we found is that inactivation caused small and statistically insignificant effects on behavior here in blue compared to control sessions in black. And my interpretation of this is that it at least shows that PPC is not an obligatory node for evidence accumulation in this task. Perhaps it plays some role that can be compensated for by other brain regions, or perhaps it's representing these variables for use for other purposes. This result has since been confirmed in monkeys using a similar manipulation, showing that monkey LIP also is not playing an obligatory role in the random dot motion discrimination task. Just to reassure you that these manipulations can have effects on behavior, and as a segue to the next part of the talk, let me show you the results for bilateral inactivation of FOF. In contrast to PPC, when we inactivated FOF, we had clear impairments in performance, as you can see here in blue, compared to the control sessions in black. The performance is getting closer to this 50% chance level. So this suggests that FOF is necessary for optimal task performance, but it doesn't tell us what role FOF is playing. Remember that the tuning curve analysis suggested that perhaps the role of FOF is not to be involved directly in evidence accumulation, but instead to report a provisional choice. That is, if the GOQ comes now, what should be chosen? And the reason for that, again, is this more step-like tuning curve, which preserves information about the sign of the accumulator value and not as much information about its graded value. But if you look at this tuning curve, you may say to yourself, hey, that's not a perfect step function. Maybe there's still enough information preserved here for FOF to play some role in evidence accumulation, or perhaps it's playing some role that's not apparent based on how we're doing this analysis. So we wanted to test this directly, and let me explain exactly how we did that. Consider again the accumulation process. We have the accumulator value as it evolves over the course of one trial that here has a duration of 1 second in length. And let me also explicitly plot the provisional choice that we think is being reported by FOF. Recall again that the choice is based on the sign of the accumulator at its present moment. So initially the provisional choice is leftward when the accumulator has a negative value. It briefly swaps to rightward when the accumulator comes to a positive value, and then it flips back to leftward for the remainder of the trial when the accumulator comes back to negative values. And here's where I want to make the most important point. For the accumulation process, history matters. If I perturb this at any point in time, it will have some effect on later results. In contrast, the provisional choice is a readout of the current value of the accumulator. So the only time period that matters in terms of behavior for the provisional choice is when that provisional choice is used to guide behavior at the end of the stimulus presentation, when the animal has to indicate its choice. So if FOF were playing some role in evidence accumulation, then perturbation of FOF at any point in time during the stimulus presentation period should have a similar result. In contrast, if our hypothesis is correct, that FOF is more closely linked to reporting a provisional choice, then there should be greater effects of perturbation at the end of the stimulus presentation than at the beginning. This is something that we tested with optogenetics, because optogenetics allowed us to do temporally precise inactivating perturbation. I'm not going to go into all the details of the methods we used for the optogenetics. I do want to acknowledge that this optogenetics experiment was led by Chuck Kopek, another postdoc in the Brody lab, who I had the good fortune to learn optogenetic techniques from that I applied to other experiments I'll tell you about later in this talk. And in this experiment, we infected FOF unilaterally with halorhodopsin using AAV under the CAMK2 alpha promoter, which selectively targets excitatory glutamatergic neurons. Halorhodopsin is a light-gated chloride pump that allows for the transient inactivation of infected neurons. And we used a similar task structure as I told you about at the beginning, with one modification, that the stimulus duration was always fixed to be 1 second in length. And then on 25% of the trials, we turned on a laser to cause inactivation for 500 milliseconds at one of 4 different epochs of the task, either just before stimulus onset here in red, during the first half of the stimulus here in orange, during the second half of the stimulus here in green, or at the beginning of the movement initiation here in blue. And again, our hypothesis predicts that the only time period that should matter is the second half of the stimulus. And indeed, that's exactly the result that was found. Unilateral inactivation before the stimulus, during the first half of the stimulus, and during the movement had no effects on behavior, whereas unilateral inactivation during the second half of the stimulus caused an ipsilateral bias. To narrow down this effect even further, we did shorter 250 millisecond inactivation, and again, only the final 250 milliseconds had a significant effect on behavior. Both of these results provide causal support for the role of FOF suggested from the model-based encoding analysis in reporting a provisional choice rather than being involved directly in evidence accumulation. So let me give a summary of the results that I've described so far. When we started these experiments, we thought that PPC and FOF in the rat may play a role in evidence accumulation just based on homology with the work in monkeys, but we didn't know that with any greater confidence. And so the first question that we want to ask is, do these regions even exhibit ramping responses during evidence accumulation as had been reported in monkeys? The answer to that question was yes, which allowed us to ask 3 further questions that went beyond any of the research that had previously been done. The first of these was, how is accumulated evidence encoded specifically in each of these regions? Are these regions causally necessary for task performance? And if so, when does the activity matter? We found that PPC has a vertical encoding of the graded value of the accumulator in terms of its average population response, while FOF has a more categorical encoding. It's not necessary for optimal task performance, while FOF is necessary for optimal task performance. However, FOF, the activity seems to matter in terms of guiding behavior only at the time of the choice at the end of the stimulus presentation period. All these results consistent with it having a primary role not in evidence accumulation. Now, I thought these results were very interesting, but at the same time, I was still wondering what areas of the rat brain may be more directly involved in accumulation. And related to this, what are the contributions of the wider network of brain regions within which PPC and FOF are connected? And so this brings me to the third and final part of my talk, applying the same set of tools to other regions within this larger network. This is a cartoon of the network that's thought to be involved in orienting control for the rat, keeping in mind that in this task, the decision is ultimately reported through an orienting movement. And I'm highlighting 2 regions in particular, the dorsal striatum, and this area I've labeled SC for superior colliculus. And the reason I'm highlighting these 2 regions is because they are the other 2 regions in which ramping responses have been observed and reported in monkeys during evidence accumulation tasks. So they're the natural next candidates to examine within this network. I should also say that all this work on the dorsal striatum and superior colliculus was done in collaboration with another postdoc in the Brody lab, Mikhail Yartsev, who now has his own lab at UC Berkeley. Starting with the superior colliculus, we targeted the deep and intermediate layers of the colliculus with coordinates shown here because those are layers thought to be involved in orienting control. And learning from my experiences with PPC, we started by doing reversible inactivation before investing in the neural recordings. And what we found is that bilateral inactivation of the superior colliculus impaired performance compared to control sessions here in black. This gave us sufficient motivation to do the neural recordings, and following the same logic as I explained to you earlier, we focused on neurons that had pre-movement side selectivity. And what we found is that these neurons have ramping profiles with slopes that depend on stimulus strength. But again, the critical question is, how do these neurons encode accumulated evidence? So we applied the same analysis as we had applied to these other brain regions using the model-based tuning curve approach. And what we found is that these neurons encode accumulated evidence relatively similarly to FOF. And what I mean by that is the values seem to cluster based on the sign of the accumulator. This becomes even more apparent if I average across time, and you can see that superior colliculus has a more step-like tuning curve. This naturally led us to believe that it may be involved not so much in evidence accumulation and, like the FOF, more involved in reporting a provisional choice, But again, we wanted to test that using our optogenetic inactivation, so we performed the same experiment. And similarly to the FOF, we found that the only time period that had a significant effect was the second half of the stimulus presentation period. So this led us to the conclusion that the superior colliculus likely has a more prominent role, again, in transforming accumulated evidence into a categorical choice rather than underlying evidence accumulation directly. And again, this was an interesting result, but at the same time I was feeling a little bit empty about the fact that we still hadn't found a region that was satisfying all of our criteria for potentially being involved in evidence accumulation directly. And that brings me to the last region that I'm going to tell you about, the dorsal striatum, and in particular the part of the dorsal striatum that receives projections from both PPC and FOF with coordinates shown here. So I'm just going to step through the same sets of experiments that I described for the three previous regions, starting with bilateral reversible inactivation. And what we found is that this caused clear impairments to behavior here in blue compared to control sessions in black, showing that this area is necessary for optimal task performance. Next, we did neural recordings, again focusing on those neurons that had pre-movement side selectivity, and we found that these responses had this characteristic of profiles with slopes that depend on stimulus strength. Again, the critical question here being, how do these neurons encode accumulated evidence? And this is where things got really interesting. These neurons have more of a graded encoding of accumulated evidence. And why is this interesting? Because this was the first brain region we'd come across that has both this graded encoding and is also necessary for optimal task performance. But we still had the critical question of, does this area contribute throughout the entire accumulation period? And so we performed the same optogenetic manipulation as we had done in FOF in the superior colliculus, and the results were different in an important way. First, similar to the other brain regions, inactivation before the stimulus presentation during the movement did not have any effect on behavior. However, what we found was that unilateral inactivation during both the second half and the first half of the stimulus presentation period both affected behavior, both caused an ipsilateral bias. And furthermore, the magnitude of this effect was similar, exactly as you'd expect from an area involved in evidence accumulation. So this has led us to conclude that the dorsal striatum is the first brain region identified in any animal model system that satisfies these three criteria for potentially being involved in evidence accumulation. It has a vertical encoding of accumulated evidence, is causally necessary for task performance, and it has a similar contribution throughout the entire accumulation period. Now I'm really excited about these results, but also a word of caution, or in terms of interpretation. I don't think that this suggests the striatum is uniquely the accumulator. Instead, what it shows us is that of all the brain regions that we've examined, it's the best bet for being involved in a larger network that underlies evidence accumulation. Finally, I'd like to summarize all the results that I've described to you in one simple slide. When I started this line of inquiry, the working hypothesis that we had was that multiple regions of the rat brain may be involved in evidence accumulation, and to the extent that they were, we thought they might have similar contributions. What we found instead is that these regions have distinct and specialized contributions. The PPC has a vertical encoding of accumulated evidence, but is not necessary for task performance. The FOF has a more categorical encoding of accumulated evidence. It is necessary for task performance, but it matters only at the time of the choice, all consistent with it reporting a provisional choice rather than being involved in evidence accumulation. The superior colliculus has a similar pattern across these three experiments, leading us to believe that it works in concert with the FOF in this task. And the dorsal striatum is the only region we've come across that satisfies all these criteria for potentially being involved in evidence accumulation. It has a vertical encoding of the accumulated evidence. It's necessary for task performance, and it matters throughout the entire period of evidence accumulation. Finally, before taking questions, I'd like to acknowledge collaborators. I've already acknowledged a number of these along the way. Former fellow postdocs of mine in the Brody Lab, Jeff Ehrlich, Chuck Kopek, and Mikhail Yartsев. I had the good fortune to work with two former talented grad students, Bing Brunson and Ann Dwan. I'd like to especially thank Carlos Brody, who is my advisor and really terrific in guiding me on these projects. I've now started my own lab at the University of California, Davis, and we have a strong and growing group. And I'd like to acknowledge funding, both past funding that supported this research and present funding that supports my lab now. Thank you very much.
Thank you. It's very interesting. I wonder, with respect to the last result, and you sort of alluded to it, it doesn't strike me that this striatum in its circuitry is a good candidate for actually maintaining information because of the way the currents are and so on. So I assume you think it's a network kind of phenomenon, like the loops or something, and there must be a cortical node, but the cortical node isn't FOF. So what do you think the circuit is going to be that, if that's how it works, and how does it work?
Yeah, I'm exactly on the same page as you. I was really shocked by this result, to be honest. I thought, we were doing striatum just in the interest of being thorough. I thought the result was going to be the same as FOF, and I thought superior colliculus would be the same. I always think of striatum as being downstream of FOF, so it seems like things are reversed. So right now our thinking is exactly in line with what you're suggesting, is that the circuitry is not the type of circuitry that you'd expect to support this persistent signal. So I think it must be through some loop that goes back to cortex and some other node in cortex. We looked at other regions of cortex that project to this area of the striatum. The ACC is a strong candidate, so that's the next region to naturally examine. But there's some other projections as well that might be good candidates here.
Thanks, Anthony. Great talk. I have a couple of questions kind of connected to. One is relating back to Yannick's talk, because you mentioned in the computational model that you have this distribution over the accumulator. And I was wondering if there's anything in your data, perhaps over multiple neurons, where you can get some insight into whether these different regions are representing a distribution over the accumulator value, similar to the way the model does. And I guess the other connected question is, do you think there will be anything different with the contribution of, say, the parietal cortex if the response wasn't binary but was somehow more graded, and then you would require that more fine-grained representation of these types?
Yeah, I love those questions. You'll like the first answer, because I think the best way to address that is to assess it directly by asking the animals to report confidence. And that's something that we're pursuing in my lab now. I think the information's there, and I think the critical question is it being used? And I would actually, and this then actually segues perfectly to your second question, I would suspect that maybe a role that PPC is playing in this task is in reporting confidence, and that's what those signals were always there for. I can give a longer answer to the second part as well. I think it probably does come down to the fact that this is a binary report, and this can explain a lot of disparate findings in the field. So when I alluded to the monkey result with inactivation, that was done in Alex Huck's lab in a similar binary report task. When I was in Mike Shadlin's lab, did microstimulation of LIP. We thought the case was closed because we had effects. It was a reaction time test, though. So now the animal has to determine when to actually report their choice. And so one of my working hypotheses is that this area is not doing evidence accumulation directly, but it's using that signal for these more complicated functions like figuring out when to stop a decision process or report confidence.
Hi, thank you for this great talk. I have two questions. Actually, I have way more, but I want to retain myself. The first one, and they are both linked, is the PPC region is the only region we see there is a kind of inhibition pattern on the primary rate after stimulus onset. So first question is, have you a hypothesis on this pattern? And second one, did you look at the effect of your causal manipulation on the reaction times of the rats?
Yeah, so I don't have a good hypothesis for the first part. I'd be interested in discussing that if you have ideas. For the second part, this is not designed as a reaction time task in the sense of a free response task. The animal cannot determine if they respond before we cue them to respond. It's that they never get reward. What we do find, what we can look at is response time from the cue. And the effects of all of our perturbation on that are relatively minor. I will say that one reason we do inactivation with optogenetics is we first tried to do stimulation with optogenetics, and we found that we would oftentimes in these brain regions, especially FOF, elicit premature responses, even when we try to use very small amounts of, titrate down the size of our perturbation. So that's an early response. You could call that a faster response time. Take that for whatever you will.
Yeah, I'd like to know if you can say much about how you think this sort of evidence accumulation paradigm should extend to when you scale to more complicated types of decision problems. And one that I'm particularly interested in is just perception of natural visual scenes, where somehow you reach a point where you decide that your perception is right, and I don't know, maybe to complicate the discussion a bit, it could be related to a problem with deep learning, where one of the fashions now is generally adversarial networks, where people have found clever ways to fool a deep network for vision and for classification into making mistakes. So it's hard to decide properly when they have the right answer or whatever. And so when you're scaling to more complicated types of problems, do you think this evidence accumulation should be something you can generalize, or do you have any idea what other kinds of paradigms might be necessary?
Yeah, so at one point I was really gung-ho about this being something that's going to help us generalize to all sorts of complicated decisions. I'm a little bit less so now, in part not because I don't think it will generalize, but I'm not sure if it gives us, I think it's too general and it doesn't give enough explanatory power. You can tweak it in many different ways to explain a lot of different type of phenomena, and I worry that we need to consider alternatives that give more explanatory power. But it is quite general. You can describe a lot of different aspects of decision making within this framework. I just wonder if it's really constraining enough, if you're interested in neural mechanisms, if it's really constraining enough in terms of the ways in which you could implement that sort of process.
Last question?
In the accumulation region that you found, do you have evidence that they do leaky accumulation?
No, in this regime, there is no evidence of leaky accumulation. That was the first result. That was not something that I was part of, but the first behavioral result. The key finding was it's near perfect integration. The time constants are longer than the longest stimuli that we use. I will say that it depends on the task. More recently, people in the Brody lab have developed newer tasks where leakier accumulation would be the more optimal strategy, and found that animals do have leakier accumulation. So it's going to depend on the task. But in this task, we don't find that.